All right, let's get right into it. For centuries, really, we've thought about medicine as a kind of war. We fight disease, we attack tumors, we battle infections. But what if that whole metaphor is just wrong? Today, we're going to explore a massive shift in how we understand our own bodies, not as a battlefield, but as the most incredible computer ever built, a computer we are finally learning how to program.
So here's the old way of thinking, right? The war on disease. It's about fighting an outside invader. But the new view, where we're headed, is completely different. It says disease isn't an enemy to be destroyed. It's a bug in our own code, a programming error. And this isn't just some nice-sounding idea. It completely changes the game. You don't drop a bomb to fix a typo. You debug the code.
This quote just nails it. If a disease is corrupted code, then the solution isn't a sledgehammer. It's a patch. A precise, elegant fix right at the source. So, how do we write that patch? And maybe more importantly, how do we deliver it?
Okay, so you've got a patch, your software. To install it, you need a delivery system. And this first part of our platform asks us to look at one of nature's oldest villains and see it as an ally. Turns out, biology has already perfected the courier service we need to get these new instructions into our cells. See, a virus isn't inherently evil. At its core, it's a molecular courier. Its danger was never the delivery truck. It was the package inside. These little machines have spent billions of years getting really good at one thing, getting into specific cells and dropping off instructions. We're not reinventing the wheel here. We're just changing the letter inside the envelope. So how do you actually turn a virus into a good guy? Well, it's this beautiful three-step process. First, you pick a virus that's already harmless, something like AAV, which, doesn't really bother us humans. Second, you gut it. You take out all its original programming. And third, you load it up with your good code, your therapeutic payload, something like CRISPR, the tool that acts like a find and replace for DNA. And just like that, the virus becomes a nanite, a tiny biological robot built to heal.
And I have to be crystal clear on this point. This is not some far-off futuristic dream. This is happening right now. This technology is in hospitals, it's approved by the FDA, it is changing people's lives as we speak. We are actively debugging human beings.
So what can this tech actually do? Well, get this. Luxturna is giving sight back to people born blind. Zolgensma is stopping a deadly disease in its tracks, in babies. And the newest one, Casgevy, is basically a cure for sickle cell disease. We're talking about a one-time treatment, and in the trials, 29 out of 31 patients were freed from the agonizing pain that had completely defined their existence. That's the power of debugging our code.
So, we have our software patch and the delivery system. That's amazing enough. But this is where the story takes a sharp turn into something truly mind-bending. We're about to talk about the hardware for this new platform, and it comes from one of the most feared and, frankly, terrifying things in all of biology.
Because think about it, right? Editing the genes we already have is one thing. But what if we could build completely new things inside our bodies? What if we could introduce a totally revolutionary new building material?
Let's talk about prions, and yes, I mean those prions, the things that cause mad cow disease. For decades, they've been the stuff of nightmares. But researchers are now looking past the disease and at the structure itself, that underlying scaffold, the amyloid. It turns out it's a programmable, self-assembling supermaterial.
Okay, don't just take my word for it. Let's look at the data. This table lines up engineered amyloid against some of the toughest materials we know. Steel, Kevlar, even the legendary spider silk. Now look at those columns, but pay close attention to the last one. Toughness. That's how much energy something can absorb before it just breaks.
160 megajoules per cubic meter. That's the number. What it means is that this biological material, this thing based on the logic of a prion, is tougher than spider silk. I mean, let that sink in. It's one of the toughest materials known to science, and it builds itself.
Oh, and it gets even crazier. This stuff isn't just tough. You can program it to be electrically conductive, essentially creating self-assembling nanowires inside the body. It can be piezoelectric, which means it generates electricity when you put pressure on it. And it is ridiculously stable. It laughs at heat, radiation, and chemicals that would destroy just about anything else.
Okay, so let's recap. We have our software, the viral nanite. We have this unbelievable new hardware, the prion supermaterial. What's missing? The interface. How do you tell this stuff what to build and where to build it?
I mean, this is the big engineering problem, right? You've got this powerful material that wants to build itself. How do you possibly control it? How do you write architecture with it and tell it, build here, but stop right there?
And the answer is just so simple and so elegant, it's beautiful. You use light. Light becomes your pen. It's the programming language for this new world of materials.
Now, it's got a fancy name, prion optogenetic lithography, but the idea is actually pretty easy to grasp. Step 1, you deliver these specially designed proteins that react to light. In the dark, they just hang out and do nothing. Step 2, you shine a very precise pattern of light, almost like a microscopic movie projector. And step 3, wherever the light hits, and only where the light hits, the supermaterial builds itself. You are literally 3D printing structures with light inside a living system. So let's just pull all these threads together for a second. We have a delivery system, we have a revolutionary building material, and we have a way to program it with light. This isn't just a new toolbox. This is a whole new relationship with biology itself. And, well, it comes with some incredibly heavy responsibilities.
Because when you combine all of this, the body stops being this fixed thing that we're just stuck with. It becomes a platform, a biological operating system that we can debug, upgrade, and even rewrite.
But look, with this kind of power, you know there are going to be some major hurdles. Of course, there are the technical risks, making sure you don't edit the wrong gene or cause a massive immune reaction. And control is everything. You don't want these things building forever. But maybe the biggest, most immediate challenge is about access and cost.
$2.2 million. That was the initial price for one treatment of Casgevy, that sickle cell cure we talked about. When a cure exists, but it costs that much, we are walking right into a future where we don't just have a wealth gap, but a biological one.
Which brings us to this final crucial idea. This isn't an if anymore. The capability is here. It's arriving. The real challenge is about us. As we are handed the quill and finally learn to write in the language of life itself, the real question is, what are we going to write? And who gets to hold the pen?